Shaky video from a handheld camera is perhaps the most obvious sign that a video is captured by an amateur rather than a professional. Traditional video stabilization techniques can remove some of that shake, but when the video contains significant parallax, such as this one, their power to stabilize is fairly limited. In contrast, 3D video stabilization techniques are designed to account for parallax and can produce results like this one from last year's SIGGRAPH. A problem with these methods, however, is that they begin by performing structure from motion to create a 3D model of the scene. Structure from motion is a slow, heavyweight algorithm that is challenged by many common properties of video, such as a lack of parallax, camera zooming, or rolling shutter. The implementation we used failed to reconstruct these sequences, for example. Our SubSpace approach to video stabilization, which we describe in the paper, combines the speed and generality of 2D stabilization with the quality of 3D video stabilization. For sequences where 3D video stabilization performs well, such as these three examples, our method produces qualitatively similar or better results. Compared to 2D stabilization, our method is better able to handle sequences captured with the rolling shutter, which is very common in newer video cameras, as well as SLR cameras that shoot video. The full-frame transforms used in 2D stabilization can remove shake, but make the wobble of rolling shutter even more apparent. This sequence is challenging for structure from motion because in-camera stabilization is used. It's also challenging for 2D stabilization because of the large depth range. Our result is much better. In this example, the scene is filled with lots of motion and is captured with a rolling shutter, both of which are challenging for 3D reconstruction. For 2D stabilization, shown on the left, the wobble from rolling shutter is again very clear. Next, we show three examples that go beyond low-pass filtering and instead fit canonical motion paths to the input. In this sped-up example, we fit a perfectly linear motion. And in this example, we fit a spline motion path. Finally, we show our simulation of a quadratic camera path. Our results are not always perfect. In this example, we can see that the sky region has some shake because its low contrast causes the number of tracks in that region to be too low for us to stabilize. Also, in the paper we refer to some results as moderately successful. Here's an example where the output is clearly better than the input, but some bounce from the original camera motion is still visible. Here are some more results. This is an example of a very long video, though we don't show all of it, that requires a streamable stabilization solution that only needs access to a local window of video frames. Our method can be run in a streaming fashion. Finally, we show two more successful results.